Okay, so we're back on weld length. So the effective length of a fillet weld measured overall length of the full-size fillet weld. Starts and stops, so forth. Space between welds determined by center to center distance of the weld, which is called a pitch. So real quick, talk about that. So if we have a weld, a 10-inch weld right here, we measure from the edge of the weld to the end point of the weld. Now let's give you a top view. So this is our T-joint plate. Okay. Now say we have a 2-inch weld with a pitch of 5. Okay. So what we need to do is we need to come in here and we need to lay down a weld that is from outside to outside 2 inches. Come over. So what I'm going to do, I want to make sure that I zoom in on this. Okay, real quick, we're doing a 2-inch weld on a 5-inch pitch. So what we just seen is that a pitch is 5 inches center to center. Okay, so real quick, we have 2-inch welds. So we know that center are automatically, if we're going to pull our measurement, we have 1 inch here and 1 inch here. So that's 2 inches out of the 5. So that tells us that our gap between needs to be 3. Our overall distance needs to be 5. Okay? Again, let's break it down. Center to center, this is 1 inch. This is 1 inch. So that's 2. So we know our distance between here and here is now 3 inches between welds. But remember, our pitch is specified center to center. So real quick, let's do it again. What if these were 4-inch welds? Okay. We still needed a 5 to be there. Okay. Half of 4 is 2. 2 and 2 is 4. So that means that our center spot now is 1 inch in between welds. You are going through the trades. You have to remember a lot of things are going to stay center line. Picking up edge finders on machinery, all off of the center line. Pipe, we stay off the center line. Always refer to the center line, and then you make your adjustments or your math accordingly from center out. Either direction, okay? Center line is key. When we build buildings, we do everything. We keep that one center line, and then we can go in or out, or we can be all on the inside. A lot of times we're going to keep thinking about center lines, okay? As you go through this program and other programs and get out there, you will know exactly what I mean when you start reading, understanding what we're talking about, and so forth. Always remember the center lines. Do your math accordingly. Occasionally you will run into something that's outside edge to outside edge, like a square building. It's going to be outside edge to outside edge, more than likely. But the plumbing work and the duct work, or the plumbing and the lines in there are going to be a center to center. Okay, weld area and stress. This is good information to know, by all means, but I don't want you to focus on this too heavy, okay? There's more important things out there. It's giving you an idea of kind of what to look at, okay? So the area is the weld length times the weld size, and the stress is equal to the amount of load divided by the weld area, okay? So I'll give you a good example real quick. What if we had 10,000 pound load and our weld area was 1 inch. Okay, 1 inch weld by 1 inch weld, 10,000 pounds. The stress is going to be 10,000 pounds. Now, where does this start going goofy? Let's look at it and say we got the same load, 10,000 pounds divided by, see if I can get it up here. See, our weld area is 1/2 inch. Okay? So first things first, 1/2 by 1/2, 0.25. So now our 10,000 pounds divided by 0.25 ends up being 40,000 pounds per square inch. Big difference, right? Let me draw this up. Instead of just talking about it, let me actually draw it up. So here we are. We have 1/2 inch weld, 1/2 inch weld. Okay? Now we're looking for our overall area. So base times height, 0.5 times 0.5 is equal to 0.25. Okay? Inches squared. Now we have 10,000 pounds of force just sitting on it. Okay? Divide that by 0.25. Very simple. 0.25 goes into 1 4 times, right? Goes into 1 4 times. If we do that, we got 10 times 4. 40,000. You can also do it on your calculator as well. So now we're at 40,000 pounds per square inch. It's a lot higher than what we thought here. It's just 10,000 pounds, right? 1 inch weld, a lot bigger weld, more surface area, correct? So now we've got only 10,000 pounds. It's important to remember sometimes things are relative. So for example, if this pin with this marker on the top, it has a little dimple on the bottom. So our surface area is a lot smaller there. 10,000 pounds on it is going to create a lot more force and a pinpoint effect, a lot more pressure per square inch there than if we were to flip it over. Now our base is bigger, the weight is spread out. Now it's 10,000 pounds per square inch, so to say. Okay? Smaller the weld, if the weight stays the same, more force. All right. Continuous weld. That's what we do in the shop for the most part. For the most part. And that's going to be from one end to the other. Now, occasionally I might tell you, weld me a 2-inch weld with a 1-inch gap, and then a 2-inch weld. So then there I would want a 3-inch pitch. Right? 1, 1, and 1. Okay? Intermittent welds, this is what we start talking about. They're a series of short welds. Page 124, spaced at intervals. So exactly what I showed earlier with the 2-1, so forth. This is an intermittent weld. They're spaced at intervals. There's another good example. Weld, space, and weld. Tack welds. Tack welds are short welds spaced at intervals to join parts. They're mainly there to hold a piece in position before you start welding the entire piece. Okay? The key point about tack welds is a lot of times welders want to come back behind the tack weld. They want to make sure they'll just fire right back up and they think they're going to burn right through the tack weld. Okay? Not necessarily true. Tack welds you usually want to grind down or prep to where you make sure you got a nice transition, just like we talked about within the fillet welds. If they're sharp, abrupt corners, grind them down to a nice easy slope so you can come weld into the weld or over the weld, and the angle is much more approachable and there's a greater chance of penetration and fusion tying into that tack weld. The other thing that's really important about tack welds is if your tack weld cracks and breaks, you need to grind it out 100%. Anytime there's a crack, you grind it out 100%. A discontinuity, grind it out. You are not going to burn it out. This is old school mentality, okay? We have found by doing non-destructive testing of x-rays and years of x-rays and ultrasound, a lot of times if they are not ground out and completely eliminated, they are still there, okay? If your tack, and this happens quite often, you'll tack something up, you'll start welding on something and you'll see a crack or a stress crack there. It may not have gave you the audible ping like bing when it cracked and shifted, but there's still cracks there. You need to make sure to grind it down 100% and start welding back over it, okay? Tack welds are a good thing, but you have to be careful how you deal with them, all right? All right. You might have a small tack weld or a larger tack weld depending on the weight and the size of the material. All right, a stringer bead. Now we're getting into our bead passes, all right? Welds made by moving weld pull along intended path in a straight line. Fast cooling rates because of faster travel speed, and it can impact grain structure and affect distortion level. Okay, let's talk about a weave bead. The weave bead is a lot wider bead. It's made by moving the weld puddle along an intended path with a side-to-side oscillation. Generally done to increase weld size. Codes, they'll allow it within a limit. Usually it's 3 to 4 times the diameter of the rod is the max amount. General rule of thumb, 1/8 inch 70/18. I usually try not to go any wider than 3/4 of an inch wide on a weave bead. Flat, I can occasionally get away with a 1 inch. Okay, 332 electrode size. I usually don't want to go much wider than 5/8 of an inch on a weave bead. The higher or the thicker the diameter of the electrode, the wider you can go, because the puddle's bigger. Okay, so it's all about the puddle size as well. And it also is a huge difference. It makes a huge difference depending on position as well. So for example, we don't weave bead anything in horizontal because guess what happens when you come up like this, the gravity's trying to pull it down. Well, then when we come down, we take a big chance of trapping slag on the bottom side of our weld. So weave beads are typically done in flat, vertical, and groove weld only of overhead. Okay? An overhead fillet weld, we do not weave bead because it's the same thing. All right? You have a T-joint like this, and if you were trying to, in an overhead position, 4F overhead position, if you were trying to weave it this way, guess what? The slag's coming to the bottom. You will have a chance of, take a big chance of trapping slag on the bottom side as well. So an overhead fillet weld, we stringer it, top to bottom. Now on an overhead groove weld, V-groove weld, yes, you can weave it side to side. Okay? I'll show you that in the shop, but it's important that you know that now. Flat welds, horizontal groove weld, we don't do any weave, stringer beads only. Okay? So, one thing I want to be clear about, how much oscillation is the difference? So a stringer bead, does a stringer bead have to be absolutely steady? Like no oscillation whatsoever, it has to be just straight? No, not necessarily. A lot of times, especially when we're going vertical, I will do a stringer bead. I consider a stringer bead to be about 2 times the diameter of the rod. Okay, 1.5 to 2 times the diameter of the rod. Basically what my weld puddle is going to be. However, I can do, even on a stringer bead, especially on vertical, I will give it a slight oscillation. It gives the edge just enough time to kind of cool down, start to solidify a little bit right before I come back to it, so I don't get a severe amount of undercut or droopiness, especially in a vertical weld position, okay, to where my weld puddle just kind of wants to fall out and run down on the other weld. So you can do a slight amount of oscillation, 1.5, 2 times max of oscillation for a stringer bead. Now it's a weave bead, again, 3 to 4 times. It's definitely a lot different, okay? The 4 basic positions: flat, horizontal, vertical, and overhead. So the flat is going to be your 1 position. 1F would be a flat fillet weld. 1G would be a flat groove weld. Horizontal, the number 2 position. 2F, horizontal fillet weld. 2G is horizontal groove weld. Vertical, number 3 position, 3F or 3G. Overhead is number 4 position, 4F or 4G. Okay? So when you look through your welding written assignments, there's a reason I put on there, instead of saying flat, horizontal, everything else, you need to understand what they mean. 1F, 2F, 3F, 4F, G. It's all part of that reading the blueprint, reading the spec that you're starting to learn. You just need to pick it up second nature. You automatically know it. We get into pipe, we'll talk about different things. So example, in pipe, we don't have a number 1, we don't have a 3 or a 4, we have a 2. We do have a 1. 1GR, or 1G, so it's considered a flat position on pipe. Usually it's when you are using a rollout wheel and you're welding it to where your welding electrode is welding flat only. You are moving the piece, you're not moving the electrode. The 2G position, your weld, remember we talked horizontal axis, right? So our weld axis is horizontal around the entire piece of pipe, okay? However, our pipe axis, it will be vertical up and down, okay? 2G weld is horizontal axis. The pipe axis is vertical. Take notes, write this down. Very important, you will see this on tests. The next one is the 6G position. This is very common with testing. It is going to be at a 45 position, so not straight up and down. You split the 90 degrees in half at 45, and your weld will be around the outside edge, okay? Give you a little better visual aid. 2G position on pipe, the weld will go around this direction. 5G, the pipe axis is vertical. 5G, the pipe axis is horizontal. Your pipe weld will be, whether it's an uphill or a downhill progression, your weld will be vertical, okay? We've talked vertical, and then remember, progression uphill, or you progress downhill, one way or the other. Then the 6G is at a 45, to where you weld either uphill or downhill as well, depending on your filler metal electrode and the procedure, okay? 2G, 5G, 6G. Okay, position used to weld from the upper side of the joint. Correct. The weld axis is approximately horizontal. This is where the terminology starts to get really goofy and you start reading technical documentation. So this is a flat position. So the weld axis will lay horizontal. However, your weld come in from flat, okay? If you notice our T-joints, lap joint, corner joint, butt joint, surface joint, okay? You see how the weld is laying flat. Horizontal, weld axis is at a point of welding is horizontal. It's the same thing I said for flat, right? See, this is where the terminology can be very goofy. If you think about it this way, Weld axis lays flat. The weld face is in a vertical plane. So what they're saying here is that it's laying vertically this way. Okay? Vertical position, again, whether it be an uphill progression or a downhill progression. Overhead. These are showing it as an isometric view, but essentially this is this. Welding on from the bottom, and so forth. From the so welding is performed from the underside of the weld joint. And again, overhead position does not mean that it always has to be over your head. If it's in this position, it can be 3 inches off the ground or 3 miles in the air. It does not matter. It's still this position. It does not matter where it is relative to your body. It's still the overhead position. 3 inches off the ground, 6 feet off the ground, or 3 miles in the air. Okay? Here's a good example, just a lot of welds to kind of get familiar with it. Groove weld, flat position. We'll get into the double V and so forth. The bottom side would have been done in an overhead. This is an overhead fillet weld. This is a lap joint in a horizontal position. Notice how it's not turned up on its edge. This T-joint is not flat, it's horizontal. Okay? This is a flat weld, horizontal, fillet weld, vertical, horizontal, horizontal, flat. 2G, 1G, 3G, and 4G. 1G, 2G, 5G, and the 1G is a flat. This ring here on this 6G is called a restrictor ring. It's used to test to see your ability to maneuver to where you don't have a complete range of motion. You need to make sure that you are able to stick at one pattern and manipulate the weld pull the way it should be. Also, a lot of times when you're doing this on this direction, 6G restrictor rings on the top side, you will have to weld this side left-handed. So for me, I'm right-handed. This would be my off side. It would be hard for me to get down here and weld this coming this way. It can be done, and I've done it before, but it's a lot easier to be able to turn it over and weld it left-handed, and then weld this side right-handed as well. Okay? If you pass the test with a 6GR, you're qualified to weld any T, K, and Y configurations within pipe fitting. That's part of the reason why you're testing that. It means that you can weld any position and also any fabricated joints, branch connections. I know this is a ton of information, but it's all good information. I really enjoy this trade. So 1F flat position, fillet weld flat versus horizontal. Look at the configuration. 3 is vertical, whether it be uphill or down, overhead. Still a fillet weld is very common in sockets, even though it's pipe. You're not doing a complete